So, hi everyone. In this video, we will learn about sub-byte function that is used in every round function of AES algorithm. So, sub-byte function acts on 128-bit string and outputs 128-bit string. Okay. So, input of this sub-byte is expressed in the form of a matrix. This matrix is of size 4 cross 4 and each element of this matrix is of 8 bit. So how many entries are in this matrix? 4 times 4 16. So 16 times 8 is 128. So total bit will be 128. So total 128 bits are arranged in this matrix, and each cell in this matrix have 8 bit of content. So what is how is this matrix prepared? So we have plain text which is transferred to my round functions. To prepare, this is the kind of input which a sub-byte takes to process it. So to build this input, we don't directly pass plain text to sub-byte. We first do some processing. So here we have, let's say this is my plain text, and in which the P0 have the first 8 bit, P1 have second 8 bit, so on. 15th 8 bit we have. Okay, so what I do, I take the first 8 bit, I'll place here in my matrix. I take second 8 bit, I place below that, and I keep on doing that column wise. So I keep on taking 8 bits from my plain text, and I keep on arranging them column wise in this matrix. First I fill this column, first I fill this column, then this column, then this column, then this column. I keep on filling each column. So I will get a matrix which is of 4 cross 4, and each entry is of 8 bit. Okay, I XOR this matrix with another K1 matrix. K1 is a key for this round function. We know that in AES we generate a key for every round function, and we generate keys for each round function by the key scheduling algorithm. So how we are getting this K1, that we will learn while we learn the key scheduling algorithm. But for now, just understand that we have a key K1 which is generated by some key scheduling algorithm for this round, and that is also of 4 cross 4. And in that key also that key is also of 128 bit. Each entry of this key1 is 128 bit. So how we are creating this key1, that we will learn in key scheduling algorithm. But when I get this K1 matrix, I do XOR of this matrix with my plain text matrix, and then I get a different matrix of 4 cross 4. Now this will serve as the input of sub-byte function. Now I will apply sub-byte on this matrix. Okay. So these are the 5 steps. Which are followed in the sub-byte function. First of all, we have a constant which is fixed. That's why it is called constant, right? So we have a 8-bit constant 0 1 1 0 0 0 1 1. In hexadecimal we can write it as 63. We can write in hexadecimal 63. So this is the constant which we use in the sub-byte function. How we are using, you will get to know. First of all, this S denotes S box. What this S box do is that it takes a 8-bit input and maps it to another 8-bit input, another 8-bit string. It outputs a 8-bit string. So what we do is that in our this input matrix, we have 8-bit in each cell. So for each cell, For these steps are performed for each cell. First we perform for S00, then S01, then S02. So these 5 steps are performed for every entry of my matrix. So let's say in general we are performing these 5 steps for an Sij entry. Let's say I took any general Sij entry or cell from my matrix, and I'm applying these 5 steps on them. So in the second step, so basically first step is nothing but declaring the constant. So I have declared this constant, and every time we take this constant only, which is fixed for the sub-byte. If you modify this, you will get some different algorithm that will not be called AES. Okay. So SBox is applied on the this Sij input, Sij entry. SBox is applied. So what SBox does is that it takes that 8 bit this Sij is 8 bit, take that 8 bit string and returns another 8 bit string which says that SBox is nothing but it's S stands for substitution. So SBox tells us that do not keep this entry, just take this entry, give it to me, I will give you a new entry which should be placed here instead of that. So instead of Sij, I will get another 8 bit number which I will place in the matrix. So how this SBox is calculating the output for a given input, that we will learn in this video only, but later. But let's say I got the input. Let's say I transferred this Sij to my SBox and I got this 8 bit string. Now what next step I will perform on this string? Now since it is a 8 bit string, I will perform operation on every single bit. So that's why I have defined a for loop from I is equal to 0 to I0 till I is equal to 7. So this 8 bit string is indexed with 0 based indexing. So index at bit at least significant position is indexed with 0, then index 1, then index 2, so on to index 7. So if I want to transform the bit at ith index, so transform bit will be bi, let's say. So and the bit which I am transforming is ai. Okay, ai is the bit at ith index in this output that we got from SBox. So what I do that I take that bit and I take the another bit which is at distance 4 from this bit. So you are incrementing index by 4. Then I take another bit that is at index 5 from that bit. So I'm incrementing 5 here in index high. Then I take bit that is at index 6 from my current bit. Then I take another bit that is at index 7 from the current bit. And here, since my bit is ith, so I will also look in my this constant term what is the bit at ith index. So let's say if I am calculating for a2, then in a2 this is 0 index, this is 0 index, this is 1 index, this is 2 index. For index 2 we have 0. So for a2 the c2 will be 0. So I'll add them up. I'll add all these bits and take the modulus with 2. So in that this is what I do for every single bit. Okay. So so I will perform this operation on a0, a1, a2, a3, a4, and a7. Also you are also seeing here modulus 8. What does it signify? This signifies that it is possible that you may on addition of 4 or 5 or 6 or 7 to my current index, you may get some index that is beyond 7, right? Let's say you have at 5 and from your I is 5. Let's say your I is 5. So you want to transform this a5 bit. So what is the bit which is at distance 4 from this bit? So since we are going from right to left, so what is the bit that is in index 4? That is distance 4 from this bit. So let's traverse 4 units in left. So from 5, this will be at 1 unit, this will be at 2 distance unit. But after that, I will just circularly move because after A7 I don't have it, so I circularly move back, and this will be at 3 distance and this will be at 4 distance. So A1 is the 4 at distance 4, A1 is at distance 4 from A5, right? Because after 7 I don't have any bit in the left direction, so we have to this we have to consider a circular rotation, circular manner in the arrangement of these bits. So after A7 just go back to the first index and keep on doing the same thing. So that's why modulus is taken here. So for A5, A5 plus 5 will be 10, and 10 modulo 8 will be what? 10 modulo 8 will be 10, or 10 modulo 8 will be 2, so that will be A2. And if I want to calculate at distance 4, 5 plus 4 will be 9, and 9 modulo 8 will be 1, so A1 is the 1 bit, A1 is the bit that is at in distance 4 from that bit. Okay, so that's why here we have placed modulo here, so that we fall back to the same set of index again and again, so that we don't get index out of bound error. Okay, so we have applied the S box on my each entry, we have applied this third operation. Now I got this bits, I got this set of bit in 8-bit string. So this is what my output of sub-byte. So from this matrix to this matrix we have performed these operations. First of all, basically we are performing major operation only in these two steps. Here in step 1 I have just written the declaration, in step 4 I have just formulating, or just I'm just writing the output, and 5 in the step 5 I am just assigning this 8-bit string to the variable Sij. So basically the actual steps are happening in step 2 and step 3. In step 2 we are applying S box, whatever output we got from S box, since S box is 8 to 8-bit mapping, so I'll get a 8 bit output from this S box. On that 8-bit string I will apply this operation. For that I will need a for loop from I0 to I7, and then the output is placed in the matrix at its corresponding position. So this is how we transform every single entry of this matrix. We take this first entry, we push it to this algorithm. This algorithm will calculate S-0 for that. Similarly, when we have S01, I'll take it, I push it to this algorithm, it will give me S-01. Similarly for S03, S11, I'll keep on giving my 8-bit string to these two steps, and they keep on getting me for S- version of that transformed 8-bit string for me. So this is how sub-byte is working. Okay, nothing very complicated till now. But so if someone says you that this is my 8-bit string, let's say someone gives you a 8-bit string and tells you that okay, find the S box output for that. Okay, so how S box is calculating output for each 8-bit string, now that we will discuss. Okay, first of all, S box maps 0 to 0. If I have a what 0 means here, 0 means I have a 8-bit string, and at every index I have 0. None of the bit is set in that 8-bit string. That 8-bit string is full of 0. That kind of 8-bit string is mapped to 0 only. So 8-bit string full of 0 is mapped with 8-bit string full of 0. Okay. Cool. But rest of the 8-bit string which are not 0, they have some other complicated operation in order to find the mapping. Okay. First of all, X is the input which I send to my S box, and it will X is not equal to 0. X is my 8-bit string, and S box will give return me Y. Y will be of 8-bit string. Okay, so you can write X as 8-bit from A0 to A7, each AI is from 0 to 1. So what we do in SBox is that, okay, take my 8-bit string and convert it to polynomial. How will you convert this 8-bit string into polynomial form? Okay, so take this bit at 0 index and make it the coefficient of make it a constant term in my polynomial. Okay, take the bit at index 1, make it the coefficient of x raised to power 1. Take this bit at index 2, make it the coefficient of x square. So bit at ith index is taken as the coefficient of x raised to power I term in my polynomial. Okay, so if I do this, I will get a polynomial. And if you observe, we have seen this form. While we were discussing the field. Okay, if you observe that this is nothing but this polynomial belongs to a standard set f2x. Now you know what is f2x. We have already defined what is f2x. f2x is the set of all those polynomials whose coefficients are taken from the field f2, and f2 is a very standard field. F2 field is defined over z2. What is z2? Z2 have integers from 0 to 2 minus 1. 2 minus 1 is 1. So we have from integer from 0 to 1 is nothing but 0 and 1. Yeah. So all the also here bit have only two possibility two values, 0 and 1. So that's why I can say that the polynomial constructed through this 8-bit string, that belongs to f2x set. If you have watched my previous videos, then you will definitely relate it with that. Okay, so just transform this 8-bit binary into a polynomial. Okay, now I got this polynomial. Now, what is the maximum degree which I can achieve on transforming this 8-bit binary into a polynomial? Since maximum index is 7 here, beyond 7 I don't have any index because we have total 8 bits. So minimum index is 0, maximum index is 7. So at max I can have degree 7 in my polynomial. If the bit at index 7 is 0, then the degree 7 will vanish. If the bit at index 6 is 0, then the degree 6 will vanish. So the maximum degree which is not vanishing, the bit corresponding to that is 1. That will be my degree of my px. So degree of my px will be less than or equal to 7. So at most I have degree equal to 7. And all those polynomials will belong to this f2x set. And you know what f2x set is. If you don't know, you can go through the previous videos of mine about field and polynomial ring, all those things. Okay, now I have this if I combine this set of polynomials with addition and multiplication operator, then it forms a field. That also we have seen in previous videos, that it forms a field. Okay, if I combine this set of polynomial with two operator plus and multiplication, I get a field. Now I'm going further in the things that we have defined in the previous videos. I will take a polynomial gx. Okay, and this gx is primitive polynomial. And now you know what primitive polynomial is. When I divide every single polynomial in f2x with this gx, when I divide every single polynomial in this f2x with gx, I got some remainders. The set of those remainders is denoted by this notation, f2x over gx. If someone writes f2x over gx, then that is a set which consists of all those remainders which I get when I divide every polynomial in f2x with this gx. So this gx is fixed. This gx is fixed for sub-byte. And this is a primitive polynomial. If you recall what is primitive polynomial is that if I take root of this equation, that root will be able to generate every other polynomial in my f2x. Okay, that root will be able to generate every other polynomial in my in this set of mine, f2x over gx. Okay. Now, if I ask you, what is the maximum degree a polynomial can have in this set? Now, I got this set by dividing every single polynomial in f2x with this gx, and this gx is having highest degree 8. So whenever I divide any polynomial px with a polynomial that has some degree n, so remainder can't have a degree beyond the divisor. The remainder can't have the degree beyond the divisor. That we also see in previous videos when we were discussing the maths prerequisites for AES. So whenever you take some degree of divisor and you divide some polynomial with that, the remainder always have degree less than equal to divisor. So the degree of the polynomials in this set will be less than 8. That is, or we can say less than equal to 7. Okay. Now we have we were having this 8-bit string. We converted to polynomial string. We got the polynomial string. We defined this set f2x over gx. Now what I want to find is that find the inverse of my polynomial under modulo gx. Okay, so let's say my px is let's say my polynomial is x4, x8, x4, x3 plus x plus 1. This is my gx. Oh, sorry, this is my gx. This is my gx, and I want to find inverse of any polynomial px under this gx operator, gx polynomial, because modulo. Since we are dividing every polynomial with gx, so the modulo is defined under this gx polynomial. So whatever polynomial you get after transforming the binary form to the polynomial form, I want to find its inverse. But I want to find its inverse under modulo gx. What is gx? Gx is x8, x4 plus x3 plus x plus 1. Now, what happen if I get the inverse of px? What kind of property inverse satisfy? If we recall the definition of inverse, we know that if I apply any qx polynomial over px under modulo this function, if I am getting 1, then that qx will be called as inverse of px. Multiply a polynomial. If you are able to find a polynomial px, on multiplying with px, I am getting something, and I am taking its modulus with this gx polynomial. By doing that, if I am getting remainder 1, by applying modulo, if I am getting output 1, then I can say that qx is inverse of px. Qx is inverse of px. Let's say this happens. Let's say qx is the 1, qx is the inverse of px, and this happens. So then what can I say? That px times qx is a product which if I divide with this gx, x8, x4 plus x3, x plus 1, I get remainder 1. So this px times qx is just 1 unit away from being a multiple of this gx. So if I subtract 1 from this px times qx, it will become a multiple of this gx polynomial, x8 plus x plus x3 plus x plus 1. Why? Because when I am dividing this polynomial, this product of polynomial, I am getting remainder 1. So let's subtract this one from this product. Then when you divide it, it will perfectly get divided with this polynomial gx. So in that case, I can say that this px times qx minus 1 is some multiple of let's say that multiple factor is hx polynomial. So this polynomial gx times some hx is equal to px times qx minus 1. Okay, now let's take one other side, one to the one side, and rest of the part of my equation some other side of the equation. So here I'm having 1, here I'm having px times qx, plus here I'm having hx times this. Now this equation is very familiar to what we see in extended Euclidean algorithm. You know what? In extended Euclidean, if you have studied extended Euclidean algorithm says that GCD of any two number, let's say a and b, can be expressed as linear combination of those two numbers. What is the linear combination of a and b? That is ax plus by. So I have expressed a and b as as a linear combination of there. So ax plus by is a linear combination of a and b. So GCD is nothing but a linear combination of those two numbers. So here you can see that, okay, this px times qx sounds like ax. It is appearing, it looks like ax. This looks like by. And here if I compare these two equation, I can say that GCD of a comma b is 1. GCD of a comma b is 1. Or I can say that GCD of px. So px is analogous to a, and this gx is analogous to b. So if and we started with the assumption that qx is the inverse of px. So if I combine these results, that GCD is 1 and qx is the inverse of px, then I can say that inverse of any polynomial px exists only when we get the GCD between that polynomial and the polynomial under which modulo is defined is 1. So when the GCD of px and this polynomial gx is 1, then only inverse is possible, because we started with this assumption and arrived to that GCD 1. So if GCD is 1, then the inverse exists. If GCD is not 1, then I'll say that no, we can't invert this polynomial. Okay, so and since it is a field, so since this combination is making a field, in field every element have inverse. If you recall the definition of field, every element have a inverse in field. So that's why we are taking this primitive polynomial and this kind of set of polynomial, so that we are able to invert we are able to find inverse of every polynomial. So it is true that for this kind of field, it is true that you will be able to find a inverse. Now, how to find that inverse? We have talked that okay, you when GCD is px and gx is 1, then that is we know that the inverse exists, and since it is a field, there will be inverse. Okay, so we don't have to worry about this GCD. But the question of the real question is that how to find this qx, how to find the inverse, if I have given some polynomial, how to find the inverse of that polynomial. So to find the inverse of a polynomial, we will use extended Euclidean algorithm. So now we will discuss the extended Euclidean algorithm to find an inverse of any polynomial. Okay. So we will come back to these points, but first of all, let's see how to find the inverse. So I am taking an example here. Let's say my px is x6 x4 plus x plus 1. So I have taken a particular example of a particular type of a particular example of px. GCD is same, gx is same, under which modulo is defined. So I want to find the inverse of this x6 plus x4 plus x plus 1 under modulo this gx. So what we do in the extended Euclidean algorithm is that make this gx a dividend. So I have, in place of dividend, I place this gx. This is gx. Make this px a divisor. So I have placed x6 plus x4 plus x plus 1 here as a divisor. Okay, now divide and find the remainder. Okay, so when you divide, it will go with x square plus 1 as quotient, and you will get the remainder x square. Now how we are dividing? How we are dividing here? You can that we have also discussed how we divide polynomials. Okay, here field is f2x. Don't forget that. Okay, so this divisor time x square is this x8, x6, x3 plus x square. Now normally you can also go through that. You can also do one thing, that subtract each term. X8 minus x is 0, x4 minus, so we will get x4 plus x3 plus x plus 1 minus x6 minus x3 minus x square. But then when you see that coefficient can't be minus 1, then you will, under modulo 2, you will make them 1. So you will get this only. So going through that subtraction way of division, instead of doing that, what you can do is that just directly add them. Then also you will get the same answer. Now x8 plus x8 will be 2x8, and 2 will become 0 under modulo 2, because field coefficient of these polynomials are taken from f2x, field f2. So and in f2 we have only 0 and 1. So 2 after taking modulo with 2 will become 0. And now here coefficient of x raised to power 6 is 0 in this dividend, and in this term coefficient of x power 6 is 1. So 0 plus 1 is 1, and 1 modulo 2 is 1 only. So I have written just simply x power 6. So use this. By doing so, you can compute the subtraction of first term and second term. So doing subtraction and then applying modulo concept, or just simply adding them, doing that we are getting same thing. Okay, so I have divided this this gx with px. Okay, so let me write it here. This is my gx and this is my px. I'm dividing and I'm getting a remainder. This is my remainder, x square. So I'm calling it r1. Let's say I'm calling it small case r1. This is my remainder r1. Now what we do is that when you get a remainder, make that remainder the new divisor. So previously we were having divisor this x6 plus x4 plus x plus. Now for further iterations, for further operation, make this remainder as divisor. This remainder will become divisor for further operation. And what will act as dividend? This divisor, which was will become my dividend now. So dividend in an iteration was a divisor in the previous iteration. So this, once I get a remainder, to proceed further, I make that remainder a divisor, and whatever I was having in place of divisor previously, now I will make it dividend, and again I will divide them. So let's considering this as divisor, this as dividend. When I divide, I am getting another remainder. So here I am getting another remainder, x plus 1. So here I was getting x square as remainder, and here I am getting x plus 1 as remainder. So let's say this is my remainder 2. Now again, for further iteration, what I will do, I will treat this x plus 1 as divisor, and now what will act as dividend? Whatever that was divisor previously. So if I go one step before, I will get x square. X square was acting as divisor. Now it will become dividend. So now I can perform division. So now what I'll get? Now I'm getting remainder 1. So this is the final remainder 1. So whenever I get remainder 1, I'll stop there and I will not move further. So this is the remainder R3. So we keep on doing this until we get a remainder 1. If we don't get remainder 1, then the inverse is not possible. Okay. So if applying this iteration, but since it is a field, and in field every element have inverse, so you will definitely find a 1 when you apply this extended Euclidean algorithm. Okay, so is it enough? No. What is inverse here? We were trying to find the inverse of px. Okay, you did this operation, you got 3 remainder. Now what is inverse? Okay, so in extended Euclidean algorithm we were having this form ax plus by, and for inverse we have 1 is equal to ax plus by. So we want to find this equation, 1 is equal to px times qx plus hx times dx. So this is my gx, this is my px, and here you can say that qx is the inverse of px. So by whatever I solved in extended Euclidean algorithm, by using that I want to create this equation, 1 plus px times hx times this. I want something like this, so that if I get an equation like this, and whatever the value of qx in that, I will say that this is the inverse of px. Okay, so you'll get it, just bear me for a moment, you'll get it. Okay, so our aim is 1 equal to qx times px plus hx times gx. You want this. If I able to find something like that, then I can say that qx will be my inverse. Okay, so px is nothing but this x6 x4 plus x plus 1, and gx is nothing but this is something that on which we define the modulo x8 x4 plus x3 plus x plus 1. Okay, how to achieve this, how to get this equation? This is our aim, this is I need to find. Okay, so we have performed this long division and we got the 3 remainder here. Now what we do is that we will backtrack, we will move bottom up, we will move from bottom to up, we will use a bottom up approach. What we do is that now in normal long division we know that remainder is equal to dividend minus divisor time quotient, but since here we are adding, instead of subtracting, we are adding. So from the operation, the kind of operation we did, we can say that remainder is equal to dividend plus divisor time quotient. So the last long division that we applied here, what is divisor? Divisor is this x plus 1. The divisor is, so in this division, last division that we performed, divisor is x plus 1. What is dividend? Dividend is x square. What is quotient? Quotient is x plus 1. Quotient is x plus 1. So what I'm saying that this remainder 1 can be expressed as dividend is x square plus divisor is x plus 1. What is quotient? Quotient is x plus 1. So I can write it like this. Is it true? You can verify. Let's try to open this right hand side. I get x square, then if I open this I'll get x square plus 1 plus 2x. This x square will get cancelled with x square, because under modulo we will get 2x square, and 2 is nothing but after modulo it will get vanished. Also this 2 will get vanished when I take modulus with 2. So this will also yield 0, and I'm getting 1 only. So I can say that right hand side and left hand side are equal. So saying this, that 1 is equal to this, the sum of these two terms, that is true. Okay. Now, what is my px? Let me write px again for the clarity. So px is x6 x4 x plus 1, x6 plus x4 plus x plus 1. What is my qx? Qx is the inverse that I need to find. So till now I don't know what is qx. I need to find qx. What is hx? Hx is some random number that I don't care about. Okay, I care about only qx. Hx come anything, I don't care about that. Gx is what? Gx already we have x8 x4 x3 x plus 1. So let me write gx also here. That is x8 x4 x3 plus x plus 1 plus x plus 1. Okay, so this is my gx and this is my px, and I want an equation 1 equal to qx time px. So I want an equation 1 equal to qx time this px plus hx, that will be anything, I don't care about that, times gx will be this. So in this equation I can't see this px, I can't see this gx, right? That means we have to work more on this equation. Okay, so here we how we got this equation? I equated this remainder with this dividend plus divisor and quotient. Okay, now let me go up let's go up and let's go one iteration back. This x plus 1 which I am taking divisor in this iteration, in the if we go upward, this x plus 1 we got remainder, we got as remainder r2 when we divided this polynomial with x square. I got this x plus 1 as a remainder when I divided this polynomial with this x square divisor. So again with the same formula, same notion, what I can say that x plus 1 is equal to dividend. What is dividend? This x6 plus x4 plus x plus 1 plus what is divisor? Divisor is x square. What is quotient? Quotient is x4 plus x square. Cool. Okay, this is the value of x plus 1. Now here I am observing that in my equation here I am having x plus 1. So I can substitute x plus 1 with this thing, right? So this is what I did. I have x square plus x plus 1. So I have substituted x plus 1 with this term, x6 plus x4 plus x plus 1 plus x square times this. Okay, now to achieve this aim I need two terms on my right hand side, and those two terms are nothing but product of some polynomial. Does it look like that? No, it doesn't look like that. Here I am having one polynomial and that is not getting multiplied to any polynomial, and here I am getting some three polynomial, this polynomial, actually four polynomial, this polynomial and this polynomial. So four polynomial which are not explicitly getting multiplied. So I'll rearrange, I'll do some shifting. Also this x6 x4 plus x plus 1 is nothing but px. So one thing is getting better, that I somehow induced my px in this equation. So here I am getting px. So let me separate this px and see what am I getting common with this px. So if I rearrange this, first of all let me open this second term. If I multiply x plus 1 with this, I will get this. If I multiply this x plus 1 with this, I will get this. Now what I'll do that, now I can see that this is my px. So and px is getting multiplied to x plus 1. So what I'll do, I keep this term and place it here. So so this looks like qx and px. Okay, but still I don't have gx here. So the rest of the term is, if I take x square common from these two terms, I get x square times 1 plus x plus 1 times x plus x square. Okay, so I simplified further and I'll get 1 plus x5 plus x3 plus x4 plus x square times x square. Okay. Let's go one more step upward. We have processed R3, we have processed R2. Now the next remainder, if we go one more step further upward, is x square. Now it's time to replace x square. So do I have x square? Yes, I have x square here. So in this equation, now it's time to replace x square. And with what you will replace substitute x square? Use this formula. Remainder is equal to dividend plus divisor time quotient. So remainder is what? X square. Dividend is what? This px. And divisor. This is what? Divisor. Dividend is this. And quotient is this. So you do this, and you'll get. So this is what I have written. This is dividend. This is divisor. This is quotient. So I have replaced x square with this term. Okay. So I got the equation. Okay. Now we can see gx. This is my gx. You see, they are equal. So gx appeared in my equation. Px also appeared in my equation. So I am very close to this, my aim. I'm very close to this, my aim. All I need to just rearrange and transform it to two terms such that each term is a product of two polynomial, right? Let's do it. So if I open the if I multiply this with this term, if I multiply this with this term, and px is appearing here, px is also appearing here, px is x6 x4 plus x plus 1, px is appearing here. So let's take this as a common. So one thing that is coming common to x6 x4 plus x plus 1 is that is x plus 1 plus this term 1 plus x plus 5 x4 plus x3 plus time plus x square times x square plus 1. So I hope you are getting this, how I go to this term. I just took common this x6 x4 x plus 1 from this term, and whatever I was getting after multiplying this term and this term, I took common x6 x4 x plus 1. Okay, I got this. Now here I am getting some addition of some polynomial, so I'll solve it further. It will look like something like this, and I'll solve it further, and it will transform it to this polynomial. Now this is my gx, and this is some hx which I don't care about. This is my px, and this is my inverse, because px is get multiplied by, if I compare it with aim, 1 is equal to qx and px. This is the term hx times gx, and the other term will be qx times px, and px is this x6 x4 x plus 1. So this term will be definitely my qx. So I can say that inverse of px is this qx, x7 x is x3 plus x. Okay, so I got the inverse of px, but okay, I got the inverse, but what now? What to do now? Convert this inverted polynomial into binary form. So if I convert this polynomial into binary form, I can say that coefficient of x raised to power 7 is 1. So at index 7 I will write 1. Coefficient of x6 is 1. So at index 6 I will write 1. Coefficient of index 5 is 0 here, so I'll write 0. Coefficient x raised to power 4 is 0, so I'll write 0 at index 4. Similarly, at coefficient of index x raised to power 3 is 1 here, so I will write 1 at index 3. So on, when I keep on doing this, I will get this binary form. Okay. So we started with px. We started with a px. We found its inverse qx. Now what was px? Px is the polynomial that we got after transforming that binary string here, that we transferred to S box here. So I told you now that S box will take one 8-bit string and output 8-bit string. So I transferred this 8-bit string to my SX. So it transformed it to a PX. And now what SBox is doing, it's finding its inverse. So first of all, it made the 8-bit string into polynomial, and then it found its inverse, and from that inverse polynomial, I again transformed it to binary, and that binary is the output of my SBox. So whatever we saw here, whatever we performed here, this is to find the output of SBox corresponding to a input PX, corresponding to a input X. Okay. So what we if I summarize what I'm doing, let's say my input is X to my SBox. First of all, I will convert to polynomial. I convert X to polynomial. Okay, I converted it to polynomial. Now I find its inverse, and now I will find its inverse. And let's say that inverse I got is QX. I will get its inverse QX. So from that inverse, I will convert it to binary. I got the binary. So whatever binary number I get, that will be my output of SBox. I hope you got it. That will be my output of SBox. So from the programming point of view, do we have to do this every time? If I have to code the SBox, if I have to code the SBox algorithm, this sub-byte algorithm, then do I have to define an SBox function? No. What we can do is that we can do some pre-processing. Okay, UR to SBox is mapping X to Y. X is of 8-bit. Y is of 8-bit. Now what are the total possible 8-bit string? That is 2 power 8, and 2 power 8 is nothing but 256. So total possible inputs are 256 only. That is not a huge number. We have total 256 inputs. So what I can do is that in advance find the output corresponding to every 8-bit string. Take a 8-bit string, find the output corresponding to it, store it in a table. Do this for every single input in this 256 possibilities. Go for each 256, go for all these 256 possibilities and find the output corresponding to each 8-bit string and store it in a table. Now once I prepare the table, I don't have to perform this again and again. I don't have to convert my 8-bit string to polynomial and find its inverse, and then from that inverted polynomial get the binary. I don't have to do it again and again. And that is done for us in textbooks. They have prepared a really good table in advance. So while coding, while implementing this in a programming language, we just use that table. We don't perform all this inverse. We don't have to do that. That was very redundant. If we do that, we just look up in that table. We will get the 8-bit input. We will look in the table. Now tell me what is the input corresponding to this output. And also this 256 is not a huge number. It will not take much space. 256 size we can prepare a table. It is not a very huge table. It will be a small table. Okay. So here is this is my table. This is my sub-byte table. This is my sub-byte table. Now how to use this table? If someone give you 8-bit string and tell you that find the output corresponding to this 8-bit string using this table, using this lookup table. So this sub-byte table is defined this sub-byte table is defined in basically hexadecimal. Okay, and now what's interesting here. This sub-byte table is not only covering SBox, it is covering all the operation that we do in a sub-byte. Okay, so you see here we first applied S box, then we applied this operation, and after that we got the S dash. So we transferred S to S box, we got some output, and then we applied this operation. So all these operations are done on prior. All these operations are done on prior. So for entire sub-byte, we don't have to do anything. We just simply use the lookup table. Give me any 8-bit input. I will give you the output of that 8-bit input. Output of sub-byte. If I apply sub-byte on that 8-bit input, I will get the output corresponding to it. I don't have to do all these things for the programming point of view. Okay. So now how to use this use this table? So you will have a 8-bit input. So convert it to hexadecimal. You know that first here if I take this 0101, this is 5 in hexadecimal, and this 0011, this is 3 in hexadecimal. So overall every 4-bit is some number in hexadecimal. So if I convert this input in hexadecimal, I get 53. So how to get the output corresponding to 53? Okay, so take the first number 5, go to the row at index 5. So this is my row at index 5. Now take the second number 3, go to the column at index 3. So this is the column at index 3. Now go to the cell which is at the intersection of this row and this column. What is that? This is this ED. This ED. So corresponding to row 5, row at index 5, column at index 3, I am getting this value ED. So output of sub-byte for 53 is ED. I hope you got it. So instead of doing all these operations from scratch, instead of taking the plain text and then with Zor we have to do that, but then applying the S box, and in S box we first convert binary bit to polynomial, then we find the inverse of that polynomial, and then convert that inverted polynomial again to binary. Then we will apply this operation on every single bit. We can do this in advance, and we instead of doing this from scratch, we can just use this sub-byte table. Just use this table and you'll get the answer of sub-byte in big O of 1 time. That quickly, yeah, very quickly you will get the answer of sub-byte if we see finding sub-byte from the programming point of view. Okay, so this was all about sub-byte. I tried my best to explain you sub-byte, but still if you have any doubt, or still if you have any query regarding sub-byte, that you can ask me in the comment section.